Good morning, mathematicians. Welcome to an office hour coming from a hotel at a conference. Why is, I don't understand the algorithm at all. Look, episode 3 has 10k views, episode 4 only 1.3. Very sad. Why is, I don't understand the algorithm. I'm just happy, I'm happy the one that did so well did so well. Hope everyone's doing well. This will be another short one today. Good morning, Edit Smith. Yeah, this will be another short one because I'm at a conference and giving a talk today, so gotta go get breakfast before everything begins. Hilarious title for a post. Hello, Astromathics. Hello, Astromathics. I guess we should probably continue with our computation from yesterday. So I have not had any time to absolve my confusions. That's not entirely true. I do think it is the case that another perspective on our ring of differentials, maybe this is exactly what people were saying yesterday, is that in this case the relative differentials should be z, it should be the original ring times dx modulo f prime dx. So I believe that's what it should be. Yeah. But we still need, the thing is that we're still looking for the annihilator within here, right? Oh, I don't think I closed my curve. How do I think about cofibrations? Map that satisfies the homotopy extension property doesn't quite cut it for me. A closed embedding, that's NDR. Well, I vaguely recall that the audio quality is way better here. Normally it's loud and there's a little reverb going on. Oh, interesting. Yeah, I mean, it's a small room. I guess normally I'm in a larger room. I wonder how much different is it between my home and the office, because some office hours I do from my office and some I do from home. What is closed embedding NDR? So yeah, I remember that there's something to do with NDR. Neighborhood retract, right. NDR pair, yeah, I vaguely recall this from Peter May's book. To be honest, I'm not the right person to ask. I don't understand fibrations very well. I mean, yeah, to me, they're just, I guess I do think about them in terms of the homotopy extension property, but I don't even, I don't work with them a lot. So, if you know about projective injective resolutions, that's how you should think about it. It's like a resolved version of a map which behaves homotopically like an embedding. Right. That makes sense, yeah. That makes sense with the vague intuition I have, but yeah. Oh yeah, I guess we'll pull up Noah Kirsch. I think it was around page 200. Somewhere here we wanted. Oh yeah, here we go. Yeah, yeah. The difference should be the annihilator of our differential map. Ah, and so the different. I mean, I guess it looks like the takeaway is that it should be. Could I bother you to take a break from this computation? Yes, because I'm stuck and confused in this computation, so I'm looking for any excuse to abandon it. TLDR and vanishing cycles. Oh no. Well, then I can't really help you. I can't help you much. Yeah, I can't say a lot about vanishing cycles. So we use them in my recent preprint. Like my research group uses the vanishing cycles functor. Well, we define this other thing, but it's more or less it's pretty much defined in terms of vanishing cycles. And what to say about it? Yeah, I feel like I don't have my head around it. You know what I mean? Like, we can do computations with them. I've done like a computation with the vanishing cycles functor, but I feel like I don't really get it. I know that it vaguely has something to do. Good morning, Beastmaster. I feel like it vaguely has something to do with Morse groups. Well, we're up to. Arad just asked about vanishing cycles, so we're talking about that as a distraction away from this what I thought was going to be a simple computation, but I just yeah, it seems like there's either ugly algebra ahead, or, well, I don't know, maybe it's easier to see it in this perspective. I don't know. Yeah. No problem. All you know is that something to do with perverse sheaves. Hello, Julie. Yeah. So I mean, yeah, exactly. Like, well, I think you can. I think you could probably apply the vanishing cycles functor to a more general complex, but yeah, usually I'm plugging in a perverse sheaf here, and I guess like there's supposed to be there's some connection with Morse groups, that there's some vague idea where, like, if you have some singularity in your space, well, there's like the vanishing cycles and the nearby cycles, and they're both related, and somehow they're like tracking the behavior of your sheaf as you go around a singularity. Sorry to bother you, but I need to tell you what's going on with f of x equals 1 x over x for all real x or not. The answer is no. The answer is no. So x over x, well, we have to be careful about what we mean. So just the symbols x over x, this does simplify. This does simplify to 1. But if you defined a function to be x over x, and you defined another function to be g, to be 1, then the question is, are these functions equal everywhere? Well, g, if you just evaluate it at 0, you get 1. That's not a big problem. But f, if you evaluate it at 0, you get 0 over 0. And this is undefined. Right? So, so as written, you don't want to substitute 0 into this equation. You'd want to simplify it first, I suppose. Yeah, what's a good way to explain this actually? The fact that it's undefined if you write it one way, but find the other. I mean, it's definitely not true. So it's definitely not true that if you plug in, it's definitely not true that 0 divided by 0 is equal to 1. That's definitely not true. It's simply an undefined expression. Yeah. Good morning, Dead Star. So I don't know if that helps answer the question. Yeah, okay. Well, I guess we could still try to finish this in the absence of further questions. I could maybe prepare a vanishing cycles computation, but also, the version of vanishing cycles I know is, in a very particular case. So there's like a bunch of theorems that are from this book of my supervisor and his co-authors, and like a bunch of very particular theorems are developed in the context that we need them. And so I don't know how well that applies to the more general case. So this should just be something like, what do I write? Z like that? Pretty common way to write the integers, I would say. I mean, yeah, I would say this is the most common way to write the integers. I mean, I don't know what other practice on the, this is how I write the math bold letters for the sets of numbers. So what are we going to have in here? I mean, this will be like the... this one looks better, you think? Well, because the top is missing there. Yeah, that doesn't look better. Maybe the real reason is that I'm lazy. So maybe I should do it more like that, so it's closed up. So here, 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 here. I don't know. I'm happy with this, to be honest. So what are we going to have? We're going to have the z-span of x and 1, but now also 2x will be 0. And that makes a lot of sense because we should have something going on with the ideal 2, I suppose, in this case. Oh, what am I saying? It should be the z-span of, I guess, both of these things times dx, right? But now we need to compute the annihilator of the image of the differential. And it seems to me like I'm tempted to think that the differential will be easier to do, or will it be harder? Actually, I'm gonna go pour myself some coffee from the machine. Okay. That's maybe a good idea. Maybe we should go instead of trying to figure out this annihilator. Chat, figure out this annihilator problem for me. Yeah, I mean, in this case, we do need to reinterpret. Right, but I mean, I think they mean like just compute, an ATAL, an ATAL, like I think they're happy to just have any example of an ATAL map. So we could do, maybe a very easy one would probably be spec QI to spec Q, right? It should be pretty easy to prove that that's ATAL. It is 2. I mean, I believe that it should be 2. That would make sense, but why? Like, what is explicitly now in this case? What is going to be our differential? Like, how does the differential behave under this description? Oh, Manju, what am I saying? I guess it's just going to be the usual thing, right? Because we're taking big. We're taking big O. So I guess our differential is just going to take a polynomial ax plus b and return a dx, right? Right. That makes sense. And then, so the annihilator then is basically going to be all, I don't know, let's call it C. So 0 to be C D ax plus b, which will be C A dx. And so it should just be 2. I mean, I could believe it should just be 2, but now if we wanted this to be 0, I mean, in order to kill this term, the C, I mean, if C was in the ideal 2x, right? If C was in the ideal 2x, that would kill it. One way to see it is the fibers of the map are Z mod P, which is separable extension, except when P equals 2. I don't see how that solves it here though. Like I'm trying to go through the description. I'm trying to go through the description of the annihilator of this map. I don't see. I could just be really smooth braining it this morning. Because this computation suggests that it should actually be the ideal 2x. Um, oh, but x is invertible. So 2x should same. Right. Okay. Haha. Okay. So, there we go. Nice. It took us 3 days, but we got there together, team. The point is that the annihilator cuts out the ramification locus inside spec C. Yeah, I mean, I agree. I think that's the thing that we were trying to I think that was the general intuition that we wanted, but it was a matter of going through this computation as explained in Neukirch, and we did it. Well, I mean, yeah. Sweet. Okay. Although, does this really? I don't know if the long extended computation, which I slogged through with a lot of help from chat, did that really help us better understand the geometry, which we wanted to? I don't know. But hopefully it's now. I mean, the initial question was just how do we geometrically interpret the discriminant, and I guess the closest thing is looking at the annihilator of your differential map. And I guess, yeah, in general, it should be some sort of ramification locus, right? Yeah. Yeah, definitely agree. Good to do such computations by hand. Okay, let's see if we can. Let's keep doing geometry, and let's answer his question about. I mean, it's close to the same example about proving that something's atal. So we could prove that this map is atal. So what do we need? We need that it's unramified and flat, right? Unless I'm mistaken, flat and unramified is enough. And for the flat part, I mean, I believe because we're just taking a map of two affine schemes, it suffices to just compute the to check the if the algebra map is flat. Well, the map on the level of rings. Rn tackling Euclidean space for the first time. Not sure if you should be looking forward to it or not. You should. You should. Yeah. Yeah. Once you understand Euclidean space, then you can understand differential geometry. So that's very exciting stuff. Finitely generated. Sorry, I don't know what part that comment was in reference to. Oh, also, I see you mentioned doing something for spec Z1 half. I don't know what you meant by that. Sorry, that was a while ago. I should have been quicker on that. Right, and so what that really means, to prove that this is flat, we just need to prove that the tensor product over here is flat, as is exact as a functor from Q modules to QI modules, right? Flatness is automatic here since every vector space is free as a module. Yeah. Yeah. Yeah, exactly. Yeah, because we can just interpret this as the two-dimensional as a two-dimensional Q module, and so. But I suppose. I mean, I agree. It's nearly exact, but I mean, technically, we're going from Q modules to QI modules. And so just saying that we have a free module. But free. Sorry, you're right. Yeah, it works either way because we're still tensoring by a free module, and tensoring. But now I'm confused. I guess the theorem should work out the same, but like I know the result. Of course, like if M is free, then tensoring by M as an endo functor from R mod to R mod. Certainly that is exact. But is it also automatic that if you like extend scalars by any free module? It should be true. Especially over vector. I don't doubt that it's true in this case, but I just wonder if there is, still something to check here. Like, what would be the general thing? Like, let R mod to S mod. F, let's say, is an SR module, which is S free. Then is this functor always exact? You can consider it as an endo functor when testing for flatness. Oh, because I could just forget back down to Q mod? I believe it, but I feel like I still want to, that all makes total sense. But I feel like I'd still want to verify it. But now I do also wonder: is this theorem true? Well, I didn't write the other part of the theorem. Implies this functor is exact. Seems like it should be. Okay, but let's take it as given for now. And then the unramified part. I forget the technical definition. Actually, I have to go right away because I have to go get breakfast before my talk. The residue field has to be a separable extension, and this pullback of the maximal ideal better be the maximal ideal. Okay, so the residue field Kx is a separable extension of Ky. Well, here our residue fields are just the fields themselves. What do we have here? How do you know by any chance? Do I know by any chance how to show that a topology induced from a countable number of semi-norms is metrizable? No, absolutely not. All that sucks was about to ask for help for something. I hope you have an amazing morning. Thanks. I hope you have an amazing morning. Yeah. Well, you can always ask in comments. You never know. Maybe I'll make a video on something. Or there's tomorrow's office hours, which will also probably be very short because I'm QI to Q is definitely not a towel. No. Well, I mean spec QI to spec Q. That's certainly a towel. That's certainly a towel. Which is like equivalent to giving it to the map Q to QI. That's what we're trying to prove is a tau. But we're going to have to do that tomorrow because it's time for breakfast. And then it's time for proofs. So go do some proofs.